Hi everyone, my name is Daifungo Liam. Today I will present my final project, Semantic Clustering and Hybrid Retrieval for Medical Questions from TF-IDF and LSA to BERT-Based Spectral Models with Reranking and Similarity Searching. For my course, CSCI E-108 Data Mining, Discovery and Exploration at Harvard Extension School, Harvard University for my Master of Data Science. So in my project, I explore how different NLP and clustering pipelines, as well as techniques of similarity search and re-ranking, behave when applied to a large corpus of short medical chatbot questions. My work spans 6 versions of clustering and 2 versions of similarity search and re-ranking, moving gradually from classical TF-IDF and latent semantic analysis into a modern transformer-based representations combined with spectral methods, similarity searching and re-ranking. My motivation is not just academic comparison. I'm interested in what kind of structure is operationally useful for the system, such as medical chatbots, triage tools, or analytics dashboards. So each version of mine reflects a design choice. How much linguistic preprocessing to apply, how to represent text semantically, and how aggressively to cluster noisy, overlapping medical content, and how effectively my model can search the similarity and re-rank all of the outputs that are predicted. So rather than claiming a single best algorithm, my project documents trade-offs across representations, clustering backends, and evaluation strategies. My final result is a clear picture of when unsupervised clustering and similarity searching and re-ranking are sufficient, and when it becomes a stepping stone toward supervised intent modeling or retrieval augmented generation, or also known as RAG. So talking about my motivation and a problem statement. Medical chatbot questions are a particularly difficult NLP domain. NLP stands for Natural Language Processing. The questions are short, informal, and often ambiguous. Many describe symptoms rather than diagnosis, and multiple medical concepts may appear in a single sentence. At the same time, the dataset includes tags that act as weak supervision, but those tags are noisy, inconsistent, and heavily imbalanced. The core problem I address is how to organize this data into clusters that are meaningful to humans, stable enough for analytics, and reducible for downstream tasks such as routing or retrieval or symmetry search and re-ranking. A naive clustering approach tends to collapse into one or two massive clusters dominated by generic symptom language like pain, test, or doctor. The guiding question throughout the project is how far supervised methods can realistically go. At what point does additional algorithmic sophistication stop helping? And when does it become necessary to introduce supervised intent models or retrieval layers? Each version of the pipeline is an experiment designed to answer that question incrementally. So my data set consists of approximately 47,600 short medical questions, each paired with a multi-label tag field. These questions resemble what user might type into a health chatbot, like short sentences, partial descriptions, and sometimes incomplete grammar. After preprocessing and POS-based cleanup, I retained 47,491 rows. Only around 112 questions are dropped, which tells me that most questions contain at least some medically meaningful signal. The tag space is large, with several thousand unique tags, but the distribution is extremely heavily tailed. A small number of tags, such as pregnancy or pain, appear thousands of times, while many tags occur only a handful of times. This imbalance strongly influences clustering and similarly social behaviors. Dense islands form around common conditions, while rare conditions tend to be absorbed into broader clusters or treated as noise, depending on the algorithm. Understanding this distribution is key to interpreting the later results. All versions of the pipeline share a common preprocessing backbone. I start with basic normalization, lowercasing text, standardizing codes and dashes, and removing extraneous punctuations. This produces a clean text field that preserves medically meaningful tokens like numbers, abbreviations, and apostrophes. Tags are parsed through using a regex approach that extracts coded strings, normalizes white space, and lowercases the results. These tags are later converted into a multi-label binary matrix. Starting in version 1.4.3, I introduced POS-based filtering using spaCy. Here, I deliberately keep only nouns and proper nouns, along with a small whitelist of short medical abbreviations such as HIV or UTI. My idea is to strip away conversational filter and focus on the representation of medical entities, body parts, and conditions. Importantly, this filtering is aggressive at the token level, but conservative at the row level, preserving nearly all questions. My project is structured as a sequence of 6 clustering versions, each intentionally modifying either the presentation, the clustering algorithm, or both. The early versions like version 1.1.3 and 1.2.3 rely on TF-IDF with latent semantic analysis and KMeans. This gives a surprisingly usable top-level taxonomy, but quickly exposes their limits, especially with very large generic clusters. In version 1.4.3, I introduced POS-based filtering and spectral clustering in the same LSA space. This sharpens themes and reduces noise, but the representation is still fundamentally linear. The version 2.x family represents a major shift. I moved to BERT embeddings combined with tag features. From there, I explore different clustering philosophies, optics to discover dense topic islands, and finally, Nyström spectral embedding followed by KMeans to achieve full coverage scale. The overarching question across versions is not which algorithm is best, but rather how different modeling choices trade off semantic coherence, interpretability, and operational usefulness. Alongside clustering, I also developed 2 versions of our Similarity search and Reranking pipeline. These are closely tied to the same representation used for clustering, which keeps the system conceptually consistent. Version 1 is a dense first retrieval model. It relies on BERT embeddings for semantic similarity and uses tag checkout overlap as a reranking signal. This works well for paraphrase queries, but can miss exact phrase matches. My version 2 introduces a hybrid design. In addition to dense and semantic similarity, it adds BM25 over normalized text. Candidate results are drawn from both semantic and lexical retrieval, and then re-ranked using a weighted blend of semantic similarity, BM25 score, and tag overlap. This mirrors how real-world retrieval systems are built. Dense models capture meaning, lexical models capture phrasing, and text help enforce intent alignment. From an architectural standpoint, clustering models evolve in 2 phases. In the V1X line, questions are represented using TF-IDF, optionally combined with tag features, and reduced via truncated SVD into an LSA space. Clustering is then performed either with KMeans or spectral clustering on that linear embedding. In the V2X line, the architecture becomes fully semantic. POS-filtered questions are embedded using a sentence BERT model, reduced with PCA, and concatenated with SVD-reduced tag vectors. This produces a compact 100-dimensional representation that blends language semantics with weak supervision from tags. For scalability and nonlinear structure, the later versions project this space into a 40-dimensional spectral embedding using a Nyström approximation before clustering. This architecture preserves neighborhood structure while remaining computationally practical. The retrieval architecture mirrors many of the same design principles, but is organized around scoring rather than partitioning. The core is a dual tower setup. One tower produces dense semantic embeddings using BERT and PCA, while the second is a lexical BM25 index built over normalized text. Texts are treated as a complementary signal. Instead of embedding them directly into the retrieval vector, I use tag checkout similarity as a transparent reranking feature. This makes it easy to inspect why a particular result ranks higher. Importantly, the semantic tower is shared with the clustering pipeline. This ensures that retrieval and clustering operate in compatible spaces, which simplifies downstream use cases like RAG or intent routing. Although this is an unsupervised project, I treat training configuration with the same rigor as a supervised model. All experiments use fixed random seeds across NumPy, PCA, SVD, landmark sampling, and clustering to ensure reproducibility. Dimensionality reduction parameters are chosen to preserve a meaningful proportion of variance while keeping the space manageable. For the Nyström spectral approximation, I sample 2000 landmarks and project the data into a 40-dimensional spectral space. Clustering is then performed using MiniBatchKMeans with multiple initialization and a K-scan. Throughout, I log runtime and intermediate outputs so that trade-offs between quality and scalability are explicit rather than implicit. The similarity search pipeline is split cleanly into offline and online components. Offline, I compute all dense embeddings, apply PCA and normalization, and build the BM25 index. This is done once and stored. At query time, the system is configurable. POS filtering can be enabled for higher fidelity or disabled for lower latency. Query vectors are then compared against the semantic index, and BM25 scores are computed in parallel. Final ranking depends on a small set of interpretable weights, controlling how much emphasis is placed on semantics, lexical overlap, and tag consistency. This makes the system easy to tune for different product needs. Because clustering is unsupervised, evaluation relies on multiple complementary signals. I compute standard internal metrics such as silhouette in the space where clustering occurs. However, these are only part of the story. To better understand structure, I also measure cosi-based cohesion and separation, as well as tag-based coherence metrics like purity and entropy. Finally, I rely heavily on human inspection, reviewing top terms, dominant tags, and example questions per cluster. In practice, this qualitative layer is critical for judging whether clusters are usable in a real system. Retrieval evaluation is handled differently because there's no ground truth relevance dataset. Instead of formal IR metrics, I rely on qualitative audits of the top results. I inspect whether retrieved questions are medically coherent, align with text, and represent plausible reuse candidates. One advantage of the hybrid design is transparency. Each result exposes a semantic similarity, BM25 score, and tag overlap, making it easy to diagnose ranking behavior. I also track offline build time and query time latency to ensure the system is realistic for production use. When comparing clustering models, clear patterns emerge. The V1X LSA-based models are easy to explain and produce reasonable top-level categories, but they consistently suffer from one or two massive clusters. Optics produces extremely clean micro topics, but labels most questions as noise, which limits its usefulness for routing. The Nyström Spectral plus KMeans approach strikes the best balance. It covers the full dataset, preserves semantic structure, and produces clusters that align well with text. For that reason, version 2.4.3 is a version I would deploy. Comparing the two retrieval versions, V2 is clearly more robust. Version 1 works well for paraphrase queries, but can miss exact phrasing. Version 2 preserves those semantic strengths while adding lexical grounding through BM25. Text then acts as a stabilizing signal that enforces intent consistency. Overall, V2 behaves much more like a production retrieval stack and is better suited for downstream applications such as retrieval augmented generation or RAG. On the clustering side, test comparison focuses less on individual queries and more on how different algorithms partition the dataset. In the early TF-IDF and LSA-based version, clusters are generally interpretable but heavily imbalanced. Test runs repeatedly show one or two megaclusters absorbing vague, symptom-based questions. When I move to optics in the BERT plus text space, the behavior changes dramatically. Test outputs reveal extremely tight, clinically specific clusters, but only for a small fraction of the data. The majority of points are labeled as noise, which limits usefulness for routing and reporting. The Nyström Spectral plus KMeans variants behave more predictably under repeated tests. Clusters remain stable across runs, cover the full dataset, and retain recognizable medical teams. Even when silhouette scores are modestly globally, per-cluster behavior during testing is consistent and interpretable, which is more valuable for real deployment. For similarity search, I compare two retrieval setups that evolve alongside the clustering pipeline. In the first version, which I refer to as V1 retrieval, ranking is driven primarily by dense semantic similarity using BERT embeddings, with tag checkard similarity acting as a secondary ranking signal. This setup works well for paraphrases and semantically similar questions, but it can miss exact phrasing or keyword-heavy matches. In V2 retrieval, I introduce a classical lexical component using BM25 over normalized text. Candidate questions are drawn from both dense semantic similarity and BM25, then merged and re-ranked using a weighted combination of semantic code size similarity, tag overlap, and normalized BM25 score. In practical tests, this hybrid approach consistently improves robustness. Exact phrases like misappeared or pregnancy test negative surface more reliably, while semantic similarity still captures paraphrases. Tags act as an intent stabilizer rather than the sole driver. Overall, V2 behaves more like a production-grade retrieval stack and aligns well with downstream rack-style use cases. For clustering, visualization plays a much more structural role. UMap projection consistently reveal a pattern of dense topic islands surrounded by a large diffuse background. This holds across LSA-based models and BERT-based models, though the island become much sharper in the embedding space. In the optics run, these islands correspond almost exactly to the clusters, with the background treated as noise. In Nyström spectral runs, the same islands are preserved, but KMeans assign background poison to broader Bayesian clusters. Dendrograms built on cluster centroids provide useful hierarchy, showing how related topics such as pregnancy, fertility, and contraception sit near one another. These visual tools help explain why some clusters have high silhouette and others do not. The data itself contains overlapping medical themes rather than clean partitions. Visualization for retrieval focuses on ranked output rather than geometric projections. I inspect tables of top K retrieved questions, along with semantic scores, BM25 scores, tag overlap, and blended scores. For text-only queries, I observe that dense semantic similarity provides a strong conceptual matrix, while BM25 reorders result to favor closer lexical alignment. For text-only queries, semantic and lexical scores collapse gracefully, and ranking becomes driven almost entirely by tag checker similarity. Mixed queries show the strongest behavior, but all three signals reinforce one another. Although I do not yet compute formal IR metrics like NDCG or recall at K, the visual inspection or retrieve neighbors show high face validity. Questions grouped together describe similar symptoms, timelines, or concerns. From a system perspective, these visual checks confirm that the re-ranking logic is behaving sensibly across different query models. The clustering demo focuses on navigation rather than ranking. A question is mapped to its assigned cluster, and I display the cluster dominant tags, top terms, and representative examples. This shows how clustering provides context that retrieval alone cannot. Even if a query retrieves relevant neighbors, knowing that they belong to a broader category like pregnancy timing, dermatology, or mental health helps with routing and analytics. In the version 2.4.3 pipeline, every question receives a cluster assignment, which makes this demo possible. In contrast, optics-based versions would leave many questions unassigned. This highlights why full coverage is an important design constraint when moving from analysis to deployment. In the similarity search demo, a user query is passed through the same preprocessing pipeline as a corpus. Depending on configuration, the query may undergo POS-filtering or simple normalization before being embedded with BERT. The system retrieves candidate questions using dense semantic similarity and BM25 in parallel, These candidates are merged and re-ranked using a blended score that combines semantic concise similarity, tag overlap, and lexical relevance. What I emphasize in the demo is transparency. Each retrieved item shows its component scores, associated tags, and original question text. This makes it clear why a particular question appears near the top. From a practical standpoint, this kind of explainability is critical if the system is to be trusted by clinicians or product teams. For clustering, the dominant insight is that medical questions do not form clean, disjoint categories. Overlap is inherent. Symptoms, conditions, and concerns naturally blur together. This explains why mega clusters appear in KMeans and why optics labels so much data as noise. These behaviors are not algorithm failures. They reflect the structure of the data. The Nyström spectral approach works well because it preserves global manifold structure while still forcing a complete partition. The result is a small number of clean, interpretable clusters alongside broader basins that absorb ambiguity. This matches how humans often reason about medical questions. Semantic structure dominates algorithm choice. Improvements is representation, POS filtering, BERT embeddings, tag features had a larger impact than switching clustering algorithms. Medical question space is inherently overlapping. Many questions naturally span multiple teams. For example, symptoms, timing, anxiety, limiting achievable global separation. Mega clusters reflect real ambiguity, not model failure. Large generic clusters capture vague or exploratory questions rather than indicating poor clustering design. Density-based methods reveal an upper bound. Optics identifies extremely coherent microtopics but sacrifices coverage, highlighting the trade-off between purity and completeness. Spectral embeddings improve manifold awareness. Nyström spectral approximation captures nonlinear structure while remaining scalable. KMeans is effective in a strong embedding space. When applied after semantic and spectral transformations, KMeans produces stable, interpretable clusters. Internal matrix must be interpreted contextually. Moderate global silhouette scores are expected in noisy, short text medical data and do not imply weak cluster quality. Tag coherence provides a valuable validation signal. Alignment between clusters and tag distributions supports semantic interpretability beyond geometric matrix. One key insight from the retrieval experiments is that dense semantic similarity alone is not enough. It excels at paraphrases, but can underweight exact wording that matters in medical contexts, such as timing or specific test names. Adding VM25 introduces an orthogonal signal that anchors retrieval to surface form, while tags provide intent-level grounding. Thus, three signals complement one another rather than compete. Another insight is that retrieval quality depends heavily on preprocessing consistency. POS filtering helps reduce noise in the corpus, but as query time, it can be optional. Making this configurable allows the system to balance accuracy and latency depending on use case. On the clustering side, the biggest success I consider was improving representation. POS filter text combined with BERT embeddings and tag features consistently outperform TF-IDF-based approaches. K-means, despite its simplicity, worked surprisingly well once applied in a good space. Spectral methods helped further by respecting the linear structure. What did not work well was expecting density-based clustering to solve everything up. Optics produced beautiful microtopics, but the lack of coverage made it impractical as a standalone taxonomy. This reinforced the idea that clustering choices must align with operational goals, not just metric performance. What worked well in Retrieval was the hybrid design, combining semantic, lexical, and tag-based signals consistently produce better results than any single signal alone. Tag checkout, in particular, proved to be a simple but powerful way to enforce intent consistency. What did not work as well was relying purely on dense similarity. With our BM25, some obvious matches were ranked too low. I also found that building dense tags embeddings without using them directly in scoring added complexity without immediate benefit. Simpler, interpretable signals often work just as well. One of the clearest lessons from the clustering side of this project is that representation matters more than the choice of clustering algorithm itself. Early on, moving from raw TF-IDF to POS-filtered text already produced cleaner and more interpretable clusters. Even before switching models, I can see that the biggest jump, however, came from moving into a BERT-based semantic space combined with text. Once the representation was strong, even relatively simple clustering methods perform well. Another important takeaway is that K-means is often underestimated. In both LSA space and spectral embeddings, K-means produce a stable and explainable top-level categories when the feature space was well designed. Finally, density-based methods like optics taught me something about data itself. They reveal how much of the corpus is fake, generic or diffuse, and how only a subset forms tight, clinically specific topics. That insight is valuable even when optics is not used for the final taxonomy. On the retrieval side, the main lesson is that pure dense similarity is rarely enough on its own. While BERT embeddings are excellent at capturing meaning, they sometimes fail to prioritize exact phrasing or repeated compliant patterns that matter in real systems. Adding BM25 in the second version made the system noticeably more robust. Lexical signals complement semantic similarity rather than competing with it. Another important lesson is the value of transparency. By exposing semantic scores, BM25 scores, and tag overlap separately, it becomes much easier to understand and debug ranking behavior. Finally, tags consistently prove useful as a form of weak supervision. Even though they are noisy, they help anchor retrieval results around consistent medical intent. Looking ahead, there are several natural extensions to the clustering work that I did. The most immediate one is human-in-the-loop refinement. The version 2.4.3 clusters form a strong proto-taxonomy, but they still need expert naming and validation from clinicians or product owners to become operational. Another direction is hierarchy. The current clusters are flat, but many could naturally be split into subtopics or grouped into higher-level categories. A hierarchical view would better support navigation and analytics. Over time, data thrift will become a concern. A production system would need periodic retraining, monitoring of cluster size trends, and alerts when new teams emerge. Ultimately, these clusters are best viewed as stepping stones toward supervised intent models rather than inputs. For similarity search, the most obvious next step is to introduce a learned ranker, such as a cross-encoder model. This would allow deeper semantic matching on a smaller candidate set. Another promising direction is cluster-aware retrieval. By restricting search to a small number of relevant clusters, both latency and relevance could be improved. Evaluation could also be strengthened by building a small label relevance set to compute metrics like precision at K or NDCG rather than relying only on qualitative inspection. Finally, the retrieval stack is well positioned to support Retrieval Augmented Generation, or RAG, where retrieved questions or answers can browse downstream language models. To summarize the clustering portion of this project, I compared 6 different pipelines across classical and modern NLP representations. My work begins with TF-IDF and LSA baselines, progresses through POS filtering and spectral clustering, and culminates in a BERT-based Nyström spectral approach. Among all versions, version 2.4.3 stands out as the best balance between semantic coherence, tag alignment, scalability, and full coverage. While no unsupervised clustering is perfect, this version produces clusters that are explainable and practically useful. From an operational standpoint, it is the version I would be most comfortable deploying as the backbone of a medical question taxonomy. On the retrieval side, the project demonstrates a clear progression from a dense-only semantic search to a hybrid retrieval and reranking systems. Version 1 establishes a clean semantic baseline using BERT embeddings and tag overlap. Version 2 adds BM25, making retrieval more robust to exact phrasing and lexical variation. The final system combines a semantic similarity, lexical relevance, and tag-based intent signals in a transparent and tunable way. Together with the clustering results, this retrieval stack provides a strong foundation for routing, analytics, and future retrieval augmented generation, or RAG, in a medical chatbot setting. This is the end of my presentation. Thank you for listening.